this is going to be my PhD defense presentation, and the topic is on the performance improvements that we want to propose for high-density wireless LAN, unplanned high-density wireless LAN deployments. Okay, now that we're in sleep mode, so I try to be as concise and fast as I can. Hopefully I can manage it well so that you don't sleep. So this is sort of like the slider that you're going to see across the presentation to show where we are. Apart from the opening and the conclusion part, this has three major parts to it. And so the first one being understanding how the high-density wireless LAN works and what might be inefficiencies that we see. And as the S's stand for solutions, two solutions that we proposed, and we hope that we'll be solving those inefficiencies that we see. So just by the name, high-density wireless LANs probably imply different things to different people. So just to set the context up, right? So I have this sort of like picture and also some of the things that we consider when we say high-density unplanned wireless LANs. So we think of these as chaotic versus planned deployments, just like access points, people just plugging in, just like your house, your neighbors. And we're thinking of them as once they're deployed somehow, they're not managed in any way. So there are no central engineering going trying to maintain them at home. So, and we think of both high density of access points as well as stations, not just like there's an access point, but there are more stations coming in. And we also think about more access points, more cells. And all this thing probably sets context for calling it more residential versus enterprise, where things would be probably well designed beforehand, well engineered, and also at the same time maintained while this thing is operating. So, and one other thing that we also right away think about high-density wireless LANs is an interference step, if you will. So, a fast motivation of are they real? How many of them are there? How does it look like today? So it's been probably like over 10 years that we started seeing these commercial units that you can buy from retail stores as Wi-Fi devices with access points, and you can just deploy them in your house. Things were good. It was convenient. Our neighbor also discovered that, but we had somewhat, available channels, so we could operate without disturbing much. Then also the others discovered the fact. Now we sort of like ended up having a interference jungle, and there are bits and pieces of information that you can find from earlier studies as to how it looks like. What are the numbers of access points that you see. You could also fire up your laptop at your house and just check the long list of access points that you scan. But we just wanted to put it into a more concise context where we go to residential area, metropolitan area, and see how many of these we actually see. And we did a passive and confidential monitoring experiment up there in Manhattan. We went to these 5 different places where these residential buildings, like tall apartment buildings and all these things are. And we were actually, after finding the maximum number of access points we didn't go with Yagi antennas or any kind of fancy stuff. We just used regular clients sitting in the car itself with regular 3 dBi rubber duck antennas and all. So we just recorded what we were seeing, and this is from one of the locations. We've seen from a single location 320 networks, individual networks, and over 220 of them were actually operating on the same channel. And I won't go into details of how we actually categorize the strong, access points and interferers. But it's actually, if you're interested, I could definitely tell you more on offline. But we can easily categorize at least over 40 of them as strong potential interferers. That they have the traffic to sort of feed their clients, they will be strongly interfering based on the RSSI you can see from the point that we were observing them. So this is sort of like, and this is the situation today. Actually, it's been some time that it's probably going worse than this. So the message I'm trying to convey is it's actually there, and these numbers are actually climbing up. So this is sort of like another picture from the individual locations as to how many you see and what are the observations. But once you sort of like draw a picture like this, you start to wonder, okay, it might be it might be a high number, but how would they perform? If they perform well, you don't care much, right? So, and going into that direction, we started looking at, okay, what would be the right places to look at for performance of this kind of a network. And the first thing is, both for historical reasons and also for the vast body of previous work went on that, was 802.11 performance models. You would probably think that, okay, I would find a good model that people worked out, and I would probably apply it for this kind of like an environment and see how it would perform. But unfortunately, majority of that we looked at are somewhat not easily applicable at all. Mostly they have assumptions on backlogged stations, meaning that all these sort of like 802.11 nodes, if you will, have packets to send out all the time. So this is somewhat like a little contrary to the typical workloads that we work with today. And also at the same time, they don't have sort of like a logical separation of an access point, a station, because it somewhat implies that you'll have an access. 802.11 DCF access is sort of like a flat scheme, right? So you don't have access point and stations a logical role on top of that. So everyone is governed by the same DCF mechanism to begin with. But having that logical role of access point actually changes the story a bit, because all the traffic has to go through that. No matter how many clients are supported by the single wireless LAN, everything is going through that, and the packets are coming in that direction. So like those logical rules are changing the way actually the workload is operating in the system also. So given that, for example, I just took it from one of those studies, but this is a typical one that you can see across all these models, where you look at the x-axis and you would see the number of stations, number of nodes, whatever you call it, increasing number of 802.11 nodes trying to use this DCF mechanism. And on the y-axis, you would see the cumulative throughput, or the system capacity, if you will. So at this point, I just wanted to make this remark of saying cumulative throughput is actually what we are using in many places across this presentation and this research, because we are interested in the system capacity. Obviously, if you have a wireless LAN or any kind of limited resource, and if you're adding sort of like elements to share it, you would expect to see a graceful sort of like scaling per node, right? So if you have 10 megabits of capacity, and if you're adding 5 nodes, obviously per node capacity will drop. And if you're adding 10, it's going to you expect it to drop gracefully. But what we're looking at here is actually the cumulative one. Normally, you would, if everything is operating well, you would expect the cumulative one to be constant. However, all these studies will tell you that you will see a annealing performance, a drastic decrease in the cumulative system throughput or system capacity as you add more nodes. And that's a well-known fact because of the fixed contention window mechanism of DCF access, since it's optimized for a certain number of nodes. If you try to go beyond that, or if you use anything that's not designed for it, you'll basically operate suboptimal. And this is a behavior that you see because of that. So should we take this as our explanation to how high-density wireless LANs will work? Each edit one, you will basically see this. For example, if I keep adding stations, should I see that? When your neighbor, for example, keeps buying notebooks, should you be seeing this or something else?
Want the exponential backlog, how this is all?
No, it's actually all the complete scheme is actually once it's a fixed contention window.
So if I collide, don't I increase my contention window?
No, you certainly do that, but so the optimal throughput that you will get from that system. So once you have that, you're actually losing that opportunity, right? You're colliding, and that's why your cumulative system throughput is dropping.
No, the cumulative should be fine, right? Because Actually I would imagine that it will just saturate. The more the numbers and the time we spend in waiting is lesser.
Well, I mean, this is actually a very well-known fact that this happens. I mean, we could go into that details if you like, maybe after this talk. But it's definitely the cumulative effect as you increase your contention window, and since it's actually, I guess the original number is somewhere between 30 or 50. I don't know, but so there's actually the number of certain number of stations that 802.11 parameters were initially told to begin with. So
the actual contention window is always reset to the minimum once you are successful. You do have some benefits with that exponential adjustment, but not as much as you would think you get. So to really address this problem, you would also have to adapt the minimum contention window with current setting, with current wireless LAN implementation.
yeah, I mean, this is sort of like a known behavior, and there are actually solutions based on contention window adaptation. One of which will come back and actually sort of like a retake on that we will present as a solution actually. But so, as I was saying, should we just assume, for example, this? Or I will show you another one from a more recent study that's showing, okay, so this is your number of nodes, and this is the cumulative system behavior. So what is different? Obviously, there are different assumptions and different way of modeling, but the primary difference between these is that the workload assumptions were different for this. So at this point, we didn't know actually what is the right model and way of assuming for high-density residential deployments, so that we can actually think about whether the system is operating at the right point or not. Can we improve it or not? So
are these comparable? In what sense are these?
So, well, they are comparable in the sense that they are both 802.11 models. They're both shooting for 802.11, for this case B. The only major difference, essentially, apart from some contention window independence, collision rate independence assumption, the major difference is actually the workload. For this case, so the classical backlogged assumption is there. And for this case, they're saying we have a TCP workload. So that's the main difference.
So is the one on the right model, or is that experimental?
So this is actually a model and a simulation of that. It's not experimental.
Oh, it's simulation.
Yeah, it's simulation.
In other words, the left one is Mac, and the other one is there's something on top of Mac.
No, this is also still, the application level throughput that you observe. But, underlying.
UDP.
You could call it UDP versus TCP also. But the point I'm trying to say is what you assume as the workload actually really changes the story, and we don't know what is there and what we should use. So with that, I just wanted to put this objective, and I'll come back and reuse it for some other stuff also. But so we wanted to understand the inefficiencies due to interference in this high-density residential setting, and we want to improve the system capacity by addressing these inefficiencies. And we want to do this by considering the existing deployments and ease of adoption for the solutions that we will propose. And we also want to think the available resources that are made available to us, like number of available channels, and also wide link capacities to these access points. So this is actually insightful in understanding why some of the previous work were not actually needed to be worked on to sort of like address this objective. So with that, I just wanted to do a very quick related work overview. At this point in time, I believe putting them into, at least from the perspective of this research, putting them into sort of like two classes is fair, where we look at some classes like studies that were done up to understand how wireless LAN performance behaves, and another class on, okay, if we know this is wrong, then how could we fix it kind of work. I'll tell you more details on these two classes. The first class on the understanding side. So there are a couple of researchers worked on like word driving databases or measurement campaigns, that kind of studies where they try to understand, okay, where are these access points? How many of them are located? What channels do they use? And how do they look in sort of like conference and campus type scenarios? So there's like a group that gives you insight on that. And there's a body of work on the enterprise domain of the picture, where they, for example, look at data collected from sensors distributed all over your enterprise, and analyze that to see if there's something going wrong in terms of the operation of your wireless LAN. Is it throughput optimal, or is there any intrusion or that kind of fault detection schemes? And also there's obviously this overall architecture of managed wireless LANs or thin access points and access point switches kind of architectures, where you have these more like dummy access points holding everything they can to a central location where you can oversee the whole enterprise and try to optimize this wireless LAN performance from that central location. And there are also a couple of protocol studies to understand how MAC performed and TCP-MAC interaction performed, or even how interference actually changed the RF and the baseband behavior. So on the recovery part, there are people who worked on outright trying to prevent and mitigate interference, which is a good thing. And it's not strictly for wireless LANs. For example, channel frequency assignment thing is like a, I don't know for how old of a problem that people are trying to solve. I just, for just fun, I found one that was from the year I was born. So, and if you just take that paper and replace the words of, for example, radio relays as base stations, and I don't know, the radios as your wireless LAN or whatever devices, it actually reads quite relevant, and you can actually challenge any recent paper with that paper. I mean, it's sort of like quite old problem, and it's evident that it's channel and frequency assignment is one orthogonal direction that should be always looked for. And more towards the wireless LAN side, there are AP selection, load balancing, kind of studies where you try to distribute your load so that your interference is evened out. And similarly, like again, an older technique, channel and frequency hopping is also another technique that you try to make these access points or interferes hop across a certain number of channels so that you can even out the interference. And on the centralized wireless LAN side, people were looking at scheduling and transceiver parameter optimization based on this centralized knowledge and the wireless LAN switches. And another class for sort of like on.
Since you mentioned hopping, who invented frequency hopping?
I can make a guess. It would probably be a military guy or some military.
Make a guess.
An actress?
Yes.
Oh,
Hollywood actors.
But from the back in the day.
well,
What's her name? Eddie Lamar.
oh, okay. Yeah. Well, I mean, yeah. It's as you go past certain dates, things really get interesting.
But you were close. She was married to a military physicist.
Okay. So, and the last class was on overhauling the 802.11 MAC, taking it completely out and putting like a collision avoidance scheme altogether, or coming up with a power control integrated into the MAC, which is actually interference aware, so that you can change the power to sort of mitigate the interference to begin. So, okay, why I went through that is, okay, given that knowledge, do we still need to do something else? I mean, does it really, at least given our objective, does it really address what we want to do? So I've taken pieces from our objective and sort of like tried to look at how this related work categorization sort of like goes there. For example, consider we have a certain number of available wireless channels, right? So we certainly think that channel and frequency assignment, selecting and access points and distributing your load across the access point is definitely the right thing, and it's definitely complementary. But in the end, it will have a limited benefit because the demand for the channels is much higher than what we have, and at the rate things progress, it looks like it's going to be like that for some foreseeable future. So for that reason, no matter what you do, you will end up having maybe an even distributed interfering scenario, right? And for again, if you think about your wired link side, most of these centralized wireless LAN schemes where they try to plug a thin access point through a gigabit connection to a centralized switch, and they try to pull every packet out of that, and then look at the packets on the centralized switch. It's prohibitively costly to do that on your DSL link, and it's actually in some cases impossible because of the link capacity. It might be technically possible for certain cases where you can have like fiber connection, consume a lower rate wireless connection, but for most cases, for the residential deployment, it's not applicable. And when you think about compatibility with the existing deployments, saying, okay, I'll replace this with sort of TDM max scheme or anything that crosses the boundary between the silicon 802.11 silicon and firmware essentially dies, at least in terms of adoption, because you need to come up with a new silicon and do the microcode for that. That essentially never happens, although you might actually standardize. People like to use what they have for quite a long time because the semiconductor process is essentially driven by the WLANs. And on the understanding part, so the bulk of it that I refer to as enterprise domain trace analysis, it's actually quite insightful, but it's providing insights from a different environment, like where you actually engineer the thing, manage the thing, and you still try to find what's going wrong and try to fix things, versus a completely chaotic environment where people just turn the thing on and you don't know what the workload is and everything. You try to understand how to use it. So it's sort of like the baselines are quite different. So with that, I want to go into understanding what we have part, starting with this principal question of, we want to understand this unplanned residential high-density wireless deployments with multiple access points on the typical workload that we have today, using typical wireless LAN equipment that we use today. Okay. And with this setting, we want to see how does the system capacity behave with increasing density. And that means both increasing number of stations and increasing number of access points. So our methodology was obviously using the big grid down there. If it's good for one thing, that's for doing high density research because it's by design a high density deployment there. So we sort of like took the advantage there. And just a brief summary, like we used all the way up to 320 clients and 12 wireless LANs, sniffer per wireless LAN. We try to do it as real as possible, like a DHCP server, traffic generators, and I'll go into the traffic workload part after this. And we had like observers to see if the experiment is actually working the way we want it to work. Because once you have these number of things, stations, clients, you don't really know what's going on when you do the experiment. You really need to keep track of what's going on. So it's probably one of the largest experiments conducted with this thing. So we specifically put a special emphasis on the workload part because as I opened it up, workload makes a really big difference. So we just want to set it right and use something that is representative of what we have today. And the way we started doing that is we actually looked at probably some of your guys' traffic in a confidential way to see what kind of protocols you guys were using here, using Orbital or the WinMain, the access point. And we actually compared also to other studies, it's sort of like in agreement. But from that, we sort of like looked at, for example, the transport protocol. Turns out that 97% of the traffic that is generated by the students over here are carried over TCP. And similarly, that 75% of that TCP is actually web browsing traffic. And those kind of percentages that we drew out of that sort of like week-long trace that we captured from the lab's access point. So, and we use it to sort of like create and mimic realistic traffic on those orbit nodes. And the way we did it was, for example, the majority of the traffic is actually coming from, as you saw, web browsing. So we implemented a web browsing monkey on those guys, where it actually browses according to a sort of like well-established web model, where you actually click on a link, think and proceed a page, which is an exponential distribution, and come back and click on another one on that page. Sort of like that kind of like a monkey sits on an orbit node. If we have 100 nodes, 75 of them are actually web browsing monkeys. 20 of them are doing file transfers, and 2 of them are doing VoIP. We actually have the actual traffic sources and the actual web browser and everything. The web server that we get the pages from and everything. It's just almost as good as it gets on the testbed. And we also, since we are thinking about
how long does it take to build a setup? How long does it take to build a setup?
You mean the runtime, the experiment?
No,
the framework.
Oh, the framework. You don't want to go there.
That's exactly what I'm asking.
Yeah, I mean, yeah, it takes. It probably takes on the order of a couple months. It's at least it's non-free.
Do you investigate? I mean, it seems like this framework is useful for lots of other research projects.
Actually, I mean, at least within here we had made
It's
it
already
possible to reuse it for some others.
So I used it in my evaluation in my PhD dissertation. Incredibly useful.
But I was curious, when you started this work, you couldn't find one that somebody had already done. It seems like this would be something.
I mean,
Like
starting the experiment.
user behavior, generating traffic,
Yeah.
it seemed to be something that
That would, yeah, you
should
would
have
think
been
that
out
it's
there
obvious.
already.
Yeah, but unfortunately, once you go into experimental mode, the energy depletes so quickly. By the time people come to that stage, they have to use some traffic generator and they're done with that. So this thing itself is actually a job on its own. So people usually deplete energy at some point in time, probably, and revert to doing hyper for bulk TCP transfer and just take down that. It might be actually okay for certain cases, but the way we set this up was to leave no chance to sort of like taking the wrong workload. At least there's no such thing as wrong or right, but what is it is what we're using today. If things change tomorrow, I think these things need to be redone, and with the workload of that day, that sort of
Right, that basic diagram there, right? That basic stage of this diagram has been around for
Yeah, but that's not the only part.
60s,
So I
right?
think
So
yeah.
there is a lot hidden. I don't think he's going into my part.
Yeah,
So this is just on one particular node. Around this, there is this whole framework that we developed where you have, which takes into account node failures, which takes into account TCP-dominant logging, making sure the logging is efficient, making sure you only extract the information that you
so was the bulk of the work on that part, not on
No, for
modeling
for this research,
Yeah.
no. I mean, it's a significant part, but it's it pales in comparison. I hope. So
You made the framework, and now a next student of Marco can take it easily.
I think
If
so.
somebody from Australia
Yeah,
can
sure.
reuse it.
Yes.
I think it's the first time
I am
so
the user, so I
Yeah.
can say you can use it. So based on the tool, I just wanted to emphasize that the tool that he built was incredibly useful for high density wireless study, and it's like incredibly reliable in terms of dealing with the kind of failures that you see in the test bed. Unfortunately, that picture that you put there is not capturing the amount of work that you did behind that. Right?
I'll just keep on. So I'm going to go into the clients essentially. So we're trying to say, okay, as we add clients, how things look like. For that reason, we just wanted to make sure the way we add clients are actually realistic. So we took like a wireless LAN traces from an IETF meeting where hundreds of people showed up, and actually took just like people coming back from lunch around like 12 to 1 p.m. Took that arrival pattern of the clients, and we just made sure that we also followed that client arrival pattern to see if it makes a difference compared to springing everything up at 1 second, which is usually de facto the experiments. So, anyways, so I'll just speed up with this single access point case. There's one access point. We're trying to see how clients actually changing the system capacity. So I'm just showing you one sort of like experiment or like two reincarnations where this first one is actually, so this is your system capacity, and between the experiment start and probably the 7th minute, so this is your clients coming in according to that pattern that I described. But once they come, 127 client comes, so the system capacity is 2368 megabits per second, which is quite close to the number that you would expect from an 802.11g operating network. And
what's the theoretical maximum given all the overheads?
I believe theoretical maximum comes to somewhere around 27, if I'm not mistaken.
This is for UDP.
I'm sorry?
This is for UDP.
This one?
TCP.
No, this is TCP. So this is TCP bulk file transfers. So we're trying to also see the fairness. So for that reason, we're actually doing a uniform traffic for all clients, for this case only. And actually, so I just wanted to make the point and go depart from that, saying that actually for this case, that arrival pattern actually didn't make any difference. So no matter how they come in, so the system capacity is actually rock solid. We don't see, we tried everything from 10 to 300 clients. So the system capacity is rock solid. We don't see anything like what I showed you with the first one. So, and we even looked at the fairness among these different flows, and even the fairness number is quite high. So about 0.95 for Jane's fairness index. So
are you using from the real life captures you got in the previous slide? Are you just looking at how many users become active with?
No. For this, since I'm looking at the fairness, actually, this particular one that I took is actually the block transfer. So I'll just go into this multi-access point one where you will see that realistic traffic here.
No, the reason I asked is if you go back to the previous slide. Yeah, the first graph over there, if you're going to use that information, use that to figure out how many users are active at various points in time.
No, this is not on the number side, but it's on actually how they come into the system. At what point in time they actually turn on their wireless device and just start traffic. It's not about how many users are active. So we just use that. If you were to use, for example, 10 clients, you just take from this 10 coming from lunch. If you're going to use 100, you take 100. Only for time.
Looking at your user association.
Yeah, so exactly, association and that part. So the takeaway from this is that actually single access point wireless LAN performs quite remarkably robust. No matter how many stations you add, it actually manages it well. I'm not saying that it doesn't, gracefully scale per wireless LAN, but the cumulative system throughput is obviously rock solid. So we move to the multi-AP case. So the layout is quite similar. So this is the time where your clients are coming in, and as you can see, it doesn't look like the other one because this is actually the one that I mentioned, where you have the guys downloading stuff from web, coming back, and then that sort of like builds up as you add more. And once you get that 120, this is the place that we want to look at. This is your steady state throughput behavior. So this is what you get for single access point case, around 17. So what we do is we keep everything constant. Number of clients, workload, everything else is the same. But we just add another access point and let them associate with that. So it somewhat splits to two groups. It's usually not 100% even, but it's pretty much even. We also have some data that it's not even.
So here it is 18 and not 23 because the traffic is not.
Yeah, because the traffic is right now it's it's spiky behavior. You cannot tell.
It's not utilizing the medium fully, right?
Yeah, there are on the average it goes probably down by like 5 megabits per second because of that behavior.
Wait,
But-
so this is with the user model traffic?
Yeah.
So just moving from a steady state to this user model drop like 5 megabits.
Yeah.
Which is.
Yeah, I mean, so the only way we could have used it is to use the exact same thing and change the access point cases, and that's what we do. So the traffic.
Right, and you use a model, how big are the data sets that they're downloading? It's like web.
It's essentially, well.
Is it enough to reach the TCP steady state all the time, or? Like
No, it's not. If it was all the time, it could have been climbing up towards that value. It's definitely a random process, but it's not a random process across these tries. But given one try, it's actually, for example, I was checking what the hell was this thing, and it was actually a PPT from Dr. Ray's website, page, the ComNet class. It was a huge one. So one of the guys started downloading that at around like 5 minutes. So, you can actually connect it to.
So were the web objects that you're downloading synthetic, or were they like real pictures?
I mean, they're actual, there's a local copy of the WinLab and a couple of other web pages.
Right, so they were real web objects.
Yeah, they're real, yeah.
Most of them are very small.
Yeah.
I mean, the reason you have you suddenly had a lot of users, is that what happens?
Not actually, but certain user at that point in time.
I'm talking
over here.
Yeah.
So from this point on, everyone is actually in the system, 127. But the way they behave is some of them are going quiet, observing the web page, then coming back requesting another object. So that's sort of like the behavior there.
It's like 127 guys browsing the web page.
Starting at that point?
Yeah, all of them starting at this point. Actually, it's not all of them are web traffic, it's that distribution. There are some bulk file transfers going on for a couple, and there's a VoIP session and all these things. But we're unfortunately cannot go into that detail over here.
So how much of this traffic is downstream versus?
So, apart from the acknowledgements for the TCP, it's actually, the web browsing and the file downloads are all done. But I think somewhere I'll make that remark where independently others and also we actually tested to see if it makes a difference in the direction of the actual bulk download versus the axe. Actually, if you think in terms of collision, it doesn't make any difference because you have a TCP. But I guess we'll get there after we're done with this. So all I was saying, we keep adding access points to the setup. Everything else is the same. Now we're serving them with 2 access points, and this is what you get.
On the same channel.
On the same channel. Yeah, everything in this research is based on strong interference. We're not going into saying, okay, you have, for example, hidden nodes, or a very weak interferer. We're talking about that. Yeah, we're talking about going to Manhattan, seeing 40 strong access points. That's your next neighbor there, the guy upstairs, the guy downstairs. So with 2 AP it goes down. With 3 AP it further goes down. With 4 AP it gets down there, and this trend continues. Okay. So if you look at the state values, from 1 to 4, you're actually losing 50% of the system capacity. Okay, and this is sort of like not, at least to us, wasn't really easy to grasp at the first because so you're actually adding stations. Stations also do transmit. They might be creating interference also. What is so special about the access? You have the same workload. Right? So the remark is that we added increased access points from 1 to 4. Everything else kept the same. We lost half of the capacity. So since we know that we were doing a controlled experiment, even we actually forced a rather naive phi rate to make sure that there are no bit error induced losses. So this is how the only left alternative is the collision rate packet losses, and this is how the collision rate looks like for this experiment. This set of experiments, I should say, first. For the sake of brevity, I just put like single AP and 2 AP case across a couple of different number of stations. So if you look at, for example, 1 AP case, so the collision rate is actually quite constant, around 10%. And it actually keeps like that no matter where you go. And that's sort of like the underlying reason why you see a rock solid throughput performance for system
They're on the
capacity.
same channel, I assume.
Yes, but this is single access point.
No, I'm talking about the two.
Yes, two access points. It's on the same channel. So once you have the second access point, so it climbs 23%, and someone keeps it on that again, no matter how many stations you have. So it's sort of like if you look at a model like like Bianchi's, it will tell you, okay, give me the number of backlog stations, and I will give you the corresponding collision rate. So, and if you look at this, it's actually changing with the number of access points, not declines. Okay, and if you were to look at what number does this correspond to, if you were to take the Bianchi's model and look at the number of backlog stations, so it somewhat quite looks like for a single access point case, you have two backlog stations, at least collision equivalent to that. And for two access point case, it actually corresponds to 4. And this actually relation goes on. If you were to do the calculation, it's somewhat like there seems to be this magical by
What's
two factor.
the more formal definition of backlog?
The formal definition is that if a station has a packet to transmit whenever it has a chance to transmit, that's called a backlog. So in other words, you have saturated UDP traffic. So,
Well, okay. Like the station's trying to put a packet on the channel.
yes, yeah, whenever you sense this amount of silence, you have something to jump for.
So does it mean that TCP and UDP essentially are like the same for this case, the experimental case?
No, they're not definitely the same because, if you were to put 4, 8, 16, it would climb up.
But if you replace TCP with UDP, would you see the same thing?
Well, if you saturate, you probably, the Bianchi's model were probably verified before by others.
Same thing as what?
I mean, as TCP and UDP essentially become the same. Does it happen in experimental?
No.
Because I mean, experimental is TCP and Bianchi is kind of UDP.
Yeah.
So if you were to use UDP, you will get a result similar to what Bianchi predicts. So now, the TCP results are different, and that's one of the insights. And then I think Mesut is trying to point out a correlation here that in the Bianchi model, the packet error weight, or the UDP workload, the packet error weight depends on the number of stations in the network. You see on the graph on the right that it goes up by adding 2 stations. While in the TCP workload, you do not see that effect based on the number of stations. You have on the bottom x-axis 4, 8, 16. Look at the black graphs. Where does it change?
So is it because the base station only has the most of the traffic, and most of the time only the base station is the access point is transmitting? Is that the reason behind it?
Yeah, it certainly has something to do with it. These stations are, of course, also transmitting acknowledgments back. So
Yeah, but I mean, is it like one acknowledgement per packet or it's still with your packet?
it's one acknowledgement per packet.
Yeah, there's no shortback. So once you actually pull out
The base station has half the traffic, and that's something to do with it.
So, okay, I think I should just directly go into this. So the reason we're looking in that that relationship is, so if you have this sort of like this traditional setup where you input your contention window setting, your frame size and number of backlog nodes, your Bianchi model will give you a certain collision rate, and from which you can go to a throughput system capacity value. So what we're after is, given this kind of like a workload, can we have somewhat the number of APs put in there, and then still come up with a throughput value representative for this kind of scenario? And essentially what we were looking for was also used in some other context from a paper from Gang and Marbach, where they were looking for the fairness characteristics for 802.11 ad hoc networks. and they had this Markov chain model of TCP Reno and how it behaved in 802.11 networks. And what they, I'm not going to go into details of that model, but the essential, at least the essential part that we used from that is, what they're saying is if you have a single source 802.11 network where you have TCP flows from one source to multiple, and if you take that, the expected number of backlogged stations in that case would be 2. Okay, so I'll tell you it from the intuition front how you can actually see that, but the due diligence phase, the way they carried out looking at the Markov chain, they're actually able to come up with that 2 also. And if you were to add single flow, single source, single destination TCP flows to that, your expected backlog stations would be, this initial 2 plus 2n. So essentially, each additional cell you're adding is actually bringing in 2 more backlog stations to what you have. Essentially, ours is a trivial extension to that, saying that if you have I interfering wireless LANs, the number of backlog stations will be through I, making that connection to number of APs to the number of backlog stations over here, which in turn comes back and explains obviously this magic number 2 value over there in the previous one. So you have single access point, that means 2 backlog stations. You have 2 access points, that means 4, and goes on. So what this insight actually provides us with is quite strong. We'll use it as one of the solutions that we have to essentially fix our contention window scheme by using this. But just before going there, I have one more slide for this initial U part, where we also looked at, investigated how multimedia, VoIP, and video sessions work on high-density settings. The somewhat context is not quite suitable for that. I won't go into details, but we have seen that you can actually, with the settings that we had, we could actually support 10 video sessions and 10 VoIP calls quite gracefully. But once you start to add these access points, for example, if you go to 4, that number drops to 2 VoIP calls. And when I say, graceful or acceptable, I'm referring to mean opinion scores that we calculate on the session. Since these are actual VoIP sessions, we can record it, for example, calculate most, which is mean opinion score is an objective, subjective scoring for this kind of like that.
So, yeah, if you go back one slide, I guess. So, another way to characterize this would be to say that because TCP doesn't actually try to get on the channel except in response to an hack, B and Keen's model doesn't apply unless you take that into consideration.
Yes.
And so that's, as you add APs, you're adding simultaneous outstanding acts. Sure. And then you're adding channel.
Yeah. I mean, the intuition I was going to use is, so regardless of the number of clients it has, obviously it needs to be greater than 1, otherwise it's only access point. But think of an access point and a certain number of clients that you're adding to this setup, right? So why does it bring 2? So what was happening in the earlier case is that whatever setup you have a certain distribution of wireless LANs to the stations, right? So access points have certain channel access rate, right? So all of them are 802.11 nodes. So, and they're actually, in theory, accessing the channel quite fair, statistically fair, right? So, and since this access point has to serve at least one ACK, or if you think about the other direction, at least one segment before the next one can happen. So it takes 3 efforts for the access points to, to serve all of them so that they can come back with a single packet. Since there's an imbalance because of that, so you're adding another access point is actually disturbing the balance towards the access point. So you're exciting more stations to create more segments for ACK stack. So essentially that's why your access point and another station is being excited by adding all these.
Right. I mean, the traffic model that BAK assumes is not really valid because in order for a packet to be sent, it's all being routed through the access point. Right?
Yeah.
So you can't really get on the channel without routing this single.
Exactly. So that logical of access point and stations makes the real difference.
So then it doesn't make difference as to whether it's upstream or downstream, right?
Yes, exactly. I mean,
Independent of whether it's a single cell or a multiple.
collision rate, I mean, collision happens once the packet starts. So it doesn't, once it starts, since we're assuming strong interference, your carrier sense and everything should be taking care of the rest.
Right.
But once you collide,
I mean, another way to model it would be to say, it doesn't matter if it's upstream or downstream, it's really the number of simultaneous queues.
Exactly.
Yeah.
Exactly. And that's what this
Yeah.
model is capturing. And the other part is this easy way to say that, oh, number of backlog nodes is going to be.
Right, no, I mean, right, so depending on the number, but you could shape, you know, if you have this number of simultaneous queues, you could try to imagine shaping other, I guess you do that with your.
yeah. So, I believe I need to speed up a little bit. So, I'm sorry.
So you said the collision rate, does it immediately translate to decrease in throughput and increase in collision rate? So yeah, basically, is there a relation between duration of RTS, CTS and the packet size? Because if I have
It's not
packets, or it's a CSM?
It's, you know, it's legacy. It's not just and this is strong interference to begin with. There's no like hidden ones that you have to manage.
If you're not increasing the load, the total load as you add more access points,
Mhm.
why is the number of backlog?
So, well, when you say you don't increase the workload, so there are two loops, right? One is that you actually start a TCP session that's introducing a workload element, but there's also the TCP zone control loop as well, right? So what you don't change is the first one, but what can and actually does change is the second part, where you, if you excite it more on this side, you're actually providing more segments and AX paths. So in that respect, obviously the workload changes.
Well, that process is going to be true even if you have this single access point, because your load is determined by the activity in the client. They're the ones initiating.
Sure.
The fact that you split them over multiple access points doesn't.
No, the control is there, but what is not there is that if you have a single access point and multiple stations, so the expected number is the same. Who is being excited keeps changing, because the access point provides the ACK to this guy and maybe the other one next guy. But if you look at the average, it's 2. That one doesn't change. That's why it's actually regulating the collisions.
You can think of a single access point case, the access point almost acts like a scheduler. Since the stations will only transmit in response if they get a packet from the access point. Once you're in steady state TCP, the access point is statistically scheduling the traffic on the wireless line.
It's forcing all the acts to a single queue.
Once you add in a second access point, now you have 2 schedulers that might conflict and collide occasionally. And the more access points you add, the more significant that effect becomes.
Okay, so with that, I'll just immediately move to this first solution that we're exploiting what we have as the insight from this previous part. So different contention window adaptation schemes have been in place. People have realized that fixed contention windows is an issue with 802.11, and they have proposed different schemes to make it, adapting to the load proposed to the network. And obviously most of them based this assumption on having backlog nodes and just tie the contention window to the number of stations in the network. But what we are seeing is that actually in our setting, so the workload or the collision rate that you're observing is actually dependent on the number of access points. So we are proposing this contention window adaptation technique based on the number of active access points instead of stations. So for that, we actually took one of the state-of-the-art contention window adaptation schemes, where so this was actually for multiple queues, the 802.11e, WLAN kind of setting. But if you just reduce it to a single queue case and replace this number of stations parameter with 2 times the access point number of backlog stations with 2 times the number of access points, you get this simple centralized formula for contention window that you should set on these access points. So the way we sort of like decided to put this as a distributed algorithm was essentially exploiting 802.11h measurement reports that are defined in the standard that you can see how much channel occupation that you have, you broadcast to your neighbors, and also you can read from your neighbor's neighbor in a standard compliant way. So what we're doing essentially is exploiting that and trying to find each access point its own neighbor's visit fraction, and uses that to come up with the estimate on the number of active access points. So you can have like 5 access points, but if there are no traffic, if they're not utilizing the channel at all, then you shouldn't be taking that into account. So once you have that information, you can take it into account and come up with an estimate on the number of active access points, and just plug in the formula and put the CW mean value. So we implemented that algorithm to see how it behaved. It actually behaved quite well. So this is how it behaves in terms of collision rate. So this dotted line is the single access point baseline, which is that 11-12% thing. So this is how it behaves actually if you don't have anything. If you have this adaptation working on, there are 2 plots over here. One is actually whatever that CW formula is giving you exact, and the blue one is actually, for practical reasons, you can't put anything as CW value. It has to be multiples of 2 because of the way binary arithmetic works in the device. So, but it seems to be not a quite big limitation. So you can actually reduce the collision down to levels which actually gets reflected to throughput. So, and above and beyond that, since you have a scheme that's reducing the collision rate, the first thing to come, probably Kishore will be smiling, is the benefit that's going to come free from your sort of like misbehaving rate control algorithm. Since it's taking the collision losses as bit losses and reducing the rate, if you fix that, then you get free improvement over and above what you get from the collision reduction itself. So there's an extra 23% that we observed for the setup in that. So, okay, to summarize that, the first is solution part. So we just proposed this contention window adaptation scheme based on the number of access points instead of the number of backlog stations. And it can actually reduce the collision rate quite close to the single access point case. And our calculation for the test we had is it's very close to 80% of the loss capacity that comes back. And it also, as a freebie, helps the misbehaving rate control. If you don't have a proper rate control, then it's also fixed that to some extent. So moving on to the second part, if you have not already noticed, I'll tell you. So Wi-Fi, the scheme that we proposed just a minute ago, implies that you have to have this software change on the access point to do that. It's not as bad as changing the 802.11 and silicon itself, but still needs the ISP to invest in the firmware changes for the access point, either install the firmware and ship out these access points to customers, or just ask customers to sort of like get them and install them, which your grandmother will never do.
I mean, doesn't it also, I thought this requires the access points to actually communicate and exchange information.
Yeah.
Which is a big difference from.
Yeah, exactly. So it has to have that 802.11h support, and you also have this firmware to implement.
And you didn't investigate the impact of the malicious.
Sure. No.
No, if I were in my apartment building, I want to push a button that says give me all the bandwidth.
Yeah.
I tell the other guys.
Yeah, I mean, yeah.
I don't know.
Yeah, wireless is slippery grounds for that.
You're not only is this, I guess my point is this is not the only set of limitations. There's other, security and cooperation.
But I mean,
issues
given our objective, this is the most conflicting one in terms of ease of adoption, essentially. So that's why we wanted to have, we want to at least think along the ideas of, can we have a scheme which can recover the losses the same way it does for this, and still avoid this cost of having changes in this software of the access point. And for that, we sort of said, maybe having a client utility software on the client, at least for some of the clients, would be much better than asking the access point to handle firmware. So this is the path we were taking. So we will have a software, software that could go onto the clients. So it doesn't have to be all the clients. So it will be the clients that we will call observing clients. And we think that is feasible because a quite high number of ISP customers are actually installing the ISP kits in their softwares that they will give you like NAC screens for Comcast and Verizon. You could easily bundle that with that. But also, as long as it's free and it's improving your performance, people are usually willing to take it and use it. So with that, we actually, this scheme is based on the.
So one comment, I mean, why do you need 11 gigs? Why can't each access point sense what everybody else is doing and compute it automatically?
Well, the only thing with that is you need to know what the other guy sends. That's what gives you.
Agreed, but based on some level of activity, why can't
Yeah, I mean, you can, definitely approximate, but the bottom line is you have to have that software distributing that in settings contention window. The 11x support or not yet, it's available.
And is it only the access point's contention window that you kind of monitor?
Yes, it's only the access point contention. So coming back, so the premise with this scheme is that we want to incorporate ISP edge router serving these access points into the scheme and try to do the similar performance recovery with this scheme. And okay, here's the overview. So this is your, so if you're talking about a typical user, so the packets that are coming out of his access point will most likely be the packets that were routed from the ISP's router. We can always find, cases where you will have very high local wireless LAN traffic. But for a typical user, these packets will somewhat translated into 8 to 11 frames from the IP packets that are coming from the access point, from the ISP router. And since this whole channel interference is actually about the workload, as we discussed before, so we were saying, can we somewhat schedule these at the ISP edge router so that actually we're reducing this whole channel interference in the air? Normally, the traditional way of doing it is obviously having a scheduled map, doing these things in tight synchronization, having clock synchronization on the radio devices itself, having very tight control on what goes up, and then you're approaching towards a TDMA kind of a thing or a TDMA overlay kind of a thing where you control it. That obviously requires a new map. But we're thinking, can we still get reasonable gains because of this regulation and get away with using not maybe that small of a time slot, but maybe a larger, but still that could go with the TCP, not break the TCP operation. Okay, that's the sort of like premise. So it aims to recover that by reducing the losses. And what we are thinking about in terms of scheduling at the ISP edge router are the packets that are for bulk traffic. So when I say that, that's sort of like open to discussion in terms of what is bulk traffic. We look at this as protocol based. For example, I'm not touching your VoIP traffic port XYZ versus your HTTP download versus this. We can always say, you can go fancy ways of having stateful packet inspection or like, context-based routers and try to understand exactly what it is. But still, even at the protocol level, we believe that controlling only the bulk packet flow is good enough. So what it does is it gives exclusive routing to those access points that it believes to interfere with. Okay, so for example, maybe that was my dissertation. Sorry. So if some oracle tells me that these two guys are interfering, then what I want to do is actually serve this guy sometime, switch to this guy sometime, switch to this guy, and I'm hoping that the way they will translate into the packets in the air will reduce the collision. Okay. And there's some extra benefit that comes free with this is it's actually working towards sharing, increasing the per wireless LAN capacity share. If you have a customer that's actually starving because of the way that it's located in the building, what you're doing is essentially creating some access in favor of that guy.
So is it sufficient to just manage the amount of traffic that's getting sent to each access point, or is your solution dependent on even managing the interpacket?
Well, it's essentially works almost like a TDM scheduler. So what you're, I mean, I'll go into this, maybe it'll, you know.
Not shaping, it's more managing the interpacket. Well, the first one is easier to implement. If all I need to do is manage how much traffic I send to an access point, that's a lot easier to do. Absolutely.
So this is how we essentially designed this. So this is your ISP edge router exploded over there, and it's how it looks like. So this is your uplink traffic that we don't mess with at all. And this is the packet that are coming from the internet towards your interfering devices. And we have this packet filter / scheduler on that path. Okay? And suppose that this part of the picture, which I'll explain, creates your schedule. Then this part is actually doing that schedule. Given a schedule, if I see a packet for this guy, and if it's the time for that guy, I'm just letting it go. Otherwise, I'm just storing it in the packet buffer until the time for that guy comes back. Okay. So how do I get that schedule? So it's sort of like based on this observing station feedback, and that feedback includes light messaging, including averaged RSSI from the access points I see. This is RSSI messages, typically a couple of seconds per message. And piggybacking at the end message, for example, every 5th or 10th RSSI, periodic RSSI report, you're adding the number of beacons you saw from an access point. Since beacons have a sequence number, and you also know the frequency at which you see these beacons, you can actually estimate the beacon loss rate from the access points. Okay. So these two things we use in these 3 functional blocks to come up with a schedule. So the first of those functional blocks is creating and refreshing a conflict map. That conflict map is telling you, okay, I have this, as an ISP, I have this bunch of access points. Which of these access points should be scheduled together? Okay. So the next functional unit is telling me how long should I give access exclusive routing to one router. I will go into details of these 3 things, which will hopefully be more clear. And the third and last one is, before creating the exact schedule to work on it, is the order in which you should do this. You have a list of access points, and you have time to give them, and should you just randomly process them, or should there be an order in which you should actually go and process the packets for those? And does it make a difference? So, and this last one is creating that order and creating the schedule. And this thing is actually periodically repeated to capture changes in the network.
So just understanding better, when you say I'm scheduling the access point, means the router is sending them a packet at
Yes.
that slot. Is that what you mean?
Yeah, exactly. So the IP packets are coming in. If I didn't have it, it would just go through. Right now, I'm looking at the schedule, and I'm either storing it if it's not the time slot for that access point, and otherwise, if it's the time slot for that one, I'm letting it go.
Okay. And the assumption is that all processing is kind of deterministic. For, when the packet comes to the access point has a certain time that it's going to send out.
No, the only part that's deterministic is once this part is telling you about a certain time slot that each access point should have. So that in absolute time is deterministic. But how things come in, for example, assume you essentially set the time for one access point and there's nothing coming in. You can always implement the timeout and switch to the next one. You don't have to wait for the whole schedule if there are no outstanding packets waiting for it to be processed.
So in some way, the access point has one packet to process, and that time that it will process that packet is just like interpret. It's going to take
The
a
access
certain
point or the
time.
router?
Sorry?
You mean the access point or the router?
I'm saying the route, right?
Okay.
It gets, in that time slot gets a packet, and it it hopefully has cleared up its queue and will process this packet in a sort of deterministic time.
I'm not sure if I fully grasped it. So when I receive a packet at this router, so the only decision that I have to make, I mean, apart from the routing delay it already has, right? It has to look up prefixes and send it, you know, select which outgoing line it should go to, right? So apart from that processing, what this is adding is either zero, I mean, negligible processing for comparison, time slot, or plus a, as you said, a deterministic delay that adds to it.
So I can understand why you're using beacon reception as reports. How does the RSS side that?
I think so. I'll start with these three units, and I think it will become clear. So, and actually, so that sort of like lists the challenges we have with this HeedNet. So, why do we have to pick the ones that we should schedule? Well, if you essentially pick all the APs you have, you might be including the ones that are not actually interfering. That will reduce your spatial reuse. And if you actually make it too small, you might exclude interference. So you want to make this list as accurate as you can with the observing stations that you have. So, and what should be that value of scheduling? That's also very important. If you pick a very small value, what you will be essentially doing is almost no scheduling, because we'll be sending out packets and immediately switching to the next guy. And in the end, these will be sort of like queuing up in the access point, so they will have frames to collide, and they will be competing anyway, so you're not creating that exclusive serialization effect on the access points. Versus if you select a larger one, you basically risk messing up with your transport protocol up there, waiting for this whole turn to come back for you to send more packets. So that's also a trade-off there for that scheduling. And for the last one, the ordering, no matter what you do, you will have this router with a certain delay and jitter that link, and also the access to it. That's sort of like a random process, and you don't have exact control over that. So whatever you do, there's going to be a certain amount of overlap from the access points that you schedule back to back. Right? So how can you minimize the effect of that? If you pick access points that don't look like each other, I go into the details of that. With the proper order, you can actually minimize the effect of those overlapping transmissions. So the first interference selection, we actually applied a retake on one of the recent conflict map creation algorithms. So the assumption with the CMAP from these MIT people are, it actually assumes a softmax, which gives you readily available collision rate estimate or packet error estimates, and can give you actually partly decoded frames that helps you understand what collided with what, so you can actually pinpoint and say, okay, these are my collision rates, and that gives you a lot better view onto your network. However, we only have some of the clients participating in this, so we are replacing that information with what we can get from that. And apart from that, it's the same conflict map creation algorithm. And I'm not going to torture you with that brief, but what it happens is that, assume this is my network setting, the basic setting, and I have these clients associated with these access points, and these are the other access points. These are my observing clients, and suppose the average RSSI listings that they're sending happen to be these values. For example, C1 is observing its own access point at -60 dBm, and A2 at this, A3 at this, and like that. And A5 it doesn't see at all. Similarly for C4, C4 it sees its own access point at -59, A5 at this, and A3 at this. So what this algorithm is saying it's saying you should have a budget for decoding a packet. Okay, so if you believe that your access point, the difference between the RSSI for your access point and for the others are larger than that threshold, you're saying whenever my access point is scheduled with that, this guy transmission will be gracefully decoded by me because it's over that budget. So it's going into the capture argument. You will have enough SNR budget to decode that. Otherwise, you're saying it's sort of like conservative. It doesn't have to, but If it's below that budget, you're saying, yeah, this is an interferer for me, and whenever these guys are to be sent packet stations. So in that way, each client is creating its interference list. For example, with this information, this first client's interference list will be my access point, NA2, my access point, NA3 are dangerous ones. So you're actually drawing lines for that conflict map. And similarly for C4, they'll only pick this one. So you ended up, so you merge these interference lists to create this conflict map altogether. And essentially, each connected component within the map is actually an individual station. So you believe these actually could be managed together. You could do, like, for example, 100 millisecond each, while you're doing 100, 100, 100 for tests independent of each other when it comes to station. So that's how the RSSI gets used. Obviously, there are clients for this others, and it's a very valid question to ask, how does it really change if you have all these as observers versus some of them as observers? Because it's not our selection, it's the client participation in this. So we sort of, at least with the topologies we had, we did some tests to see how actually conflict map changes if you had like 25% participation versus 50 and 100. And it seems to be like anything beyond, anything below 25% of the clients, assuming that there's an access point and station for your deployment, is quite biased. But if you have something beyond 25 to 50, you have a very good representation. Beyond 50, it actually doesn't change quite much because you're already talking about the very high density one in terms of the deployment. So I would say it's not, it's very plausible to have that, at least that much of participation. So for time slot selection, as I said, so it was a trade-off between having too small and too large. So what we did is essentially use that beacon rate as the feedback for the collision rate. So we're using a certain value for a time slot, start with that, and do a gradient, online gradient search on that value. So it initially falls quite fast. So in a couple of seconds, you actually start to operate in this range, and you try to optimize it better. And if it doesn't change more than a certain percent, just stay there. And then we restart this algorithm for searching that value. It's essentially that. And this test is actually, this is like an exhaustive test on scheduling. And this is when you start this algorithm, where it actually ends up.
So what is the equation you can use selecting a scheduling time slot based on
So in the end, what you're trying to do is to reduce the collision rate to a minimum. So that's sort of like your discriminant. And you're essentially, you have to observe for a certain number of periods. Like it's not as fast as having beacon reports. So that's why you have a certain number of beacon reports happening, and then you calculate the collision rate and decide on changing that. So for the order, as I said, the order is important because if these transmissions out of the access points will be leaking, if you will, you want them to minimize the number of collisions. And how you can do that is actually, not everything will be the same amount of interference, right? So, for example, if you are to schedule these access points like randomly, like A1, A2, A3, A4, A5, A6, versus scheduling A1 and then scheduling the one that is most alike, that doesn't look like A1 at all in terms of the observations, and then picking another one that doesn't look like this one at all, and doing that based on the signal space distance that you have from these observers, then you get to have a schedule where you sort of like schedule the access points that won't hurt their clients too much. I don't know if it follows.
So you're just trying to schedule the access points that are most dissimilar in signal space.
Yeah. So for that reason, even if you sort of like overlap a little, it's not, at least it's not as bad as picking these two side by side and moving that and just scheduling that. So I can give you some value to the gains we've seen versus random scheduling. It gives you another 20%.
Yeah, I didn't see your thesis. Is there a lot of prior work on that scheduling, or is that something like much prior work on?
Well, scheduling in terms of having it on a, like, far away on the access, on the ISP side, we don't have anything that looks much like that. But obviously, if you're talking about scheduled MAC, then there's all these fine-grained time-scheduled MACs that are available in TDMs.
Right, well, okay, this scheduling problem seems like it may have occurred before, but maybe not, which is if I'm some downstream, if I'm some networking device, and I know that if I release this packet, it may cause interference much farther downstream.
Sure.
So, certainly occurred in centralized operating plans, managed wireless lines.
Yeah, but I haven't seen much prior work on that. I mean, I'm sure it's occurred before. I haven't seen it before.
I'm saying because vendors don't publish papers.
Yeah, that's one that's going to make. I mean, people talk about that being there, but we have unfortunately no documentation.
Well, but it's not even clear they do studies, it just publish the
Okay, so moving on to.
The difference here is, again, doing it from the router at very different time scales with much less control about the timing in which the packets actually are.
Right, because it's really a probabilistic thing. It's not like they're tightly controlled.
So somehow, like if you think of each access point as a queue, you're changing the rate that comes from the rate that you fill the queue.
Sure. Yeah, it's regulating.
That's sort of
I
what.
think it's not the rate. It's still trying to affect the timing in which the packets are emitted.
But if you think of every access point sort of spinning out as soon as you can, then the only way you can modulate how frequently the access point is if you're sort of waiting till the queue is empty.
Exactly. So we're trying to
Sort of say,
trying to
if your
keep
queue is empty,
We're trying to keep the queues empty on the access points.
Interfering on pairs.
On the interfering access points, and then only
So you're-
send to one access point out of
Right.
these interferes with burst of packets.
so like what you're doing is you're trying to sort of like have two parameters. You're trying to have, okay, the access point is served at a certain rate. You're trying to sort of feed it at that rate so that it's, and also even if it's full, you're trying to sort of like empty it and then keep the rate same kind of.
Give it enough time to empty before we so switch to
And
the access
the
point.
feedback that tells you I'm empty these collisions.
Yeah, it's a cool.
Yeah, well, another way to characterize the problem was you have these interfering sets, and you want exactly one packet in each set.
Yeah, I mean, that's.
Right. That would be the ideal, right? So we can do that probabilistic, or probabilistic.
Okay, so going on to.
So, you're essentially saying that all the access points belong to one
You've got
ISP.
these end buckets.
Yeah. So the assumption with that is.
So what if we have multiple ISP, and so the conflicts in that going to be different, right?
Sure. I mean,
Handle that.
yeah. Let me expand that to a more generic term. So you can have two types of heterogeneous kind of like environments. You can say, okay, I have one ISP, but these are being served from different edge routers. That's one sort of like heterogeneous case you can have. And the other one is the more extreme one is your next neighbor is the Verizon guy, and I am the Comcast guy. How does that happen? So, essentially our take on that is, we think it's technically quite easy to address. It's more of a business and policy issue to make it happen, because it's very easy to partition scheduling space. Just like the frequency space, for example, your AT&T has a certain number of GSM frequencies, the other guy has the others. You can also say, okay, for this setting, here's our partitioning in scheduling space. Now let's just conform to that. But who would follow that? Well, if I'm in the Comcast, I would probably say I have this feature and this for my users and not care about the other guy. That's what probably will happen. But it's sort of like under a category of technically easy, realistically more work needed, or at least intent for cooperation needed from ISPs. As long as it's there, it's very easy.
So you could potentially fit that same problem maybe or the way by having the guys report the RSS size of the access points they see, and there are certain access points that you cannot control, right? So maybe as a simulation you can say that okay, this percentage of access points you cannot control, and then see what happens.
Yeah,
your
it's essentially,
scheduling can.
yeah, it'll hit the point between no one's participating and everyone's participating. You will essentially degrade as you have more that you can't control.
Well, it also causes a prisoner's dilemma problem. By not participating, I'm actually going to get more.
Yeah. Yeah, actually, I mean, wireless is a somewhat interesting field where you have a lot more examples of that.
You have to be able to penalize.
Okay, so this is the way we took for the evaluation of this. We did like we actually went out. So we started with the Manhattan case. So we went there and looked at the apartment databases and see what would be like typical residential apartments and what would be the size, number of floors, number of units per floor, kinds of information, and classified that as like 3 apartment settings: small size, medium size, and large size. Small size, with the number of access points on the same channel becomes not so interesting. We also looked at the Beagle.net database to see what are the current percentages of access points being on the same channel. Turns out to be the largest chunk on the channel 6 is on 35%. So what we did is we essentially randomly placed an access point and station in each floor, and then selected random 35% to be interfering ones, and then worked on this data set for the simulations to be more realistic. And the workload and the topology for that looks like you have 10 megabit DSL kind of links where you have around 1 millisecond plus a random jitter kind of a delay for your ISP edge router to your access point, and you have like 100 megs length around the ISP edge router to the servers that you operate with. And the workload that they're actually testing is they're just downloading a large file kind of workload. I'll just skip the smaller details. And we still have the same setup of DHCP, and we use it per second as a warm-up, and we report the averages and 95 percentiles from these experiments. And the wireless part is 8 to 11 Gbps. Yeah, great job. So jumping up to the first result is, so this is the medium-sized apartment case where where it happens to be 7 wireless LANs, 7 units, 7 people, interfering in the apartment. In the large case, it's out of I guess 170 something units, 50 of them actually are interfering. So this is what you have if you don't do anything. For the experiment, this is in terms of the number of bytes transferred for a fixed amount of simulation time, which is 2 minutes. So you actually recovered quite some, even with the 7 case. And with the large apartment case, you're actually seeing 2.2 times increment in the system capacity if you also do this schedule. And looking a little bit to back, I won't spend too much time, but it's coming from, again, reduced collision rates that you can achieve with this. So for example, large case, so the baseline for single access point collision rate is around 10%, as we already discussed. So this is going down from all the way to 60 to 10% by doing this. And there's also a slight fairness improvement also that we discussed at the beginning. So I think the next question the careful listener will probably ask is, okay, how about the delay behavior? Because you're scheduling these things back to back. 2 questions coming is, does that break my TCP session? Is the first thing, right? Because I give like 100 milliseconds to this access point, and in my case, I have 50 access points. So I'm coming back and 50 times 100 millisecond and serving this, right? Assuming everyone has practiced this. So does it affect the TCP behavior? I mean, if you think first just on that number, you can say, oh, it might actually break it. But if you look at how TCP is operating with the baseline, it's actually so bad, so that having this actually improves it quite some. So, for example, I have the TCP trace for one of the flows in this evaluation, So what this is the top part is the data segments, and the bottom gray ones are the ACKs coming from the other direction. And so this is the 2-minute 2-minute download when you have nothing, the legacy system. And for this size of a download, this is how much it takes with the HeedNet. Okay, so it finishes at 86 seconds. So if you look at this, you can actually see quite large intervals where the station is actually starving. So although you're not doing any scheduling at all, but that increases 60–70% collisions are actually getting into this. So you start hitting timeouts for TCP, and you have all these dead intervals anyway. So
are those dead intervals definitely due to timeouts, or is it just saying the RTT super high or something?
Well, I mean, it's connected.
When you get a timeout, then the RTT will go.
Yeah.
Shoot it up.
Yeah, exactly. I mean, by the time you retry it, it turns out to be quite large interval. So, and if you look at this, so what you receive is actually more regular, frames, and since you have a lot less collision, and you turn out to be both not affecting TCP and also completing the whole transfer in less time. So it's sort of like counterintuitive at first look, but it actually makes sense.
Did you actually try to add up those gaps and see if they match?
Yeah, probably. Yeah.
I mean, you're doing like TDMAs.
Yeah. Yeah, TDMA.
Sort of like
yeah, it's more like a rough attempt for it. Yeah. And the last part, we actually took this and implemented it. The way we did is we actually took the click router from MIT, which is like a Linux router on steroids kind of a thing, where you have quite this, easy to grasp scripting language where you can bypass the Linux networking stack and put your own logic for quite fast routing, quite fast in my sense, not maybe Ivan's sense, but at least less than 100 megabits per second is quite doable. So how it works out in our deployment, I'll go into details of that in the next slide, but we have this general purpose rack server we have over here. On one end, it's connected to the internet. So as you can see, the uplink direction, we don't do anything. It just bypasses from device to device. And on the downlink direction, when you receive packets, you actually, so painting in click terms is actually labeling the coming packets. So you're painting the packets based on destination IP, which means, okay, these are the ones that won't be scheduled. So if it's not on your config map, you're painting them so that when it goes to the paint switch, it just goes to the other device. And you also paint them on based of source port. That's your bulk traffic versus VoIP bypassing facility. And you also then you have a paint switch based on the destination wireless LAN. You color it with one color and put it in different queues. And you have a timer switch from which you essentially serve these queues. Yeah, it's as simple as that. It works quite. I've seen like 170 megabits that you can do with this.
You have to write your own column. I don't see you don't have to write a click module like that. Okay. In the sense, you don't have to write your own click component.
I mean, I wrote the click script for
That's
that.
fine.
Yeah, but everything else is everything else is yeah.
It makes it
Sure.
yeah, it makes it multiply.
Yeah, sure. I mean, probably. I mean, if this were to go into a production network, that would probably
It will be
be
different. But
Yeah.
still, yeah, easy.
So what we used this on was we have this. For those who know it, we have these outdoor nodes lying around in the vicinity. So we squeezed in like more consumer access points in those setups. If you look closely there, you'll see consumer access points scattered down. So like these, Cisco D-Link, Linksys, Netgear ones, just to make sure that we can actually operate with the consumer devices, actually a piece. So we have this router going to internet and connected to these, and we have 2 stations each. And the type of workload we tested was kind of like a popular one, is a YouTube streaming. So when these guys come up, they're actually firing up a browser and start watching the Obama's State of Nation in 2010 in 720p high def. which comes to around, on average, 2 megabits per second workload per streaming. YouTube streaming is kind of like hard to pinpoint, saying that it's 2 megabits per second straight, because it has its own buffering scheme with that Flash application. But on average, it comes to 2 megabits per second. And also, we tested an unscheduled VoIP session to see how it actually survives with the scheduled setup. And what we've seen is that, for example, if you look at this, so this is written without HeedNet. So if you have the HeedNet, you can actually see quite a drastic change in the average throughput that you can see. If you add the single VoIP session, it's the same. Obviously, the VoIP session has no significant amount of traffic by itself. But if you look at the most score, if you don't have the HeedNet, it's actually around fair, and actually climbs up quite nicely when you have the HeedNet, because the unscheduled traffic is also actually benefiting from the reduced collision rate environment, because it's actually using UDP, and it's quite hurt if you have a high collision environment. Okay, this finishes this part also. So just to summarize, so we actually proposed the scheme of what HeedNet, where Wi-Fi could not be adopted, and it's based on client observations and driving scheduling parameters at the ISP edge router. And we actually created what we believe to be a representative scenario for a high-density wireless LAN apartment setting, and on our evaluation on that gives us almost 73% recovery for the loss compared to baseline case, which I didn't show you over here. But if you compare that to the last data that I showed, it's 73% of the loss capacity coming back, which translated to 2.2x improvement in throughput for system capacity.
In the HeedNet algorithm, there's some parameters, right? We were looking at a collision rate, you compare that to some, what is the threshold?
Yeah.
How much did you have to tweak that? I mean, was it like pretty robust to, or did you like have to try a lot of times and find the right numbers?
Well, I mean, for the ones that have, for example, for the gradient descent, we didn't have to do much, because it was actually converging on its own. But for example, we didn't take it to an extreme where you actually keep the network changing, for example. It's converging in the order of seconds, right? For example, 10 seconds, 15 seconds. So if you were to have a changing network every second, I mean, there's no way you can actually converge to that. It's actually converging to a reasonable value quite fast, and then trying to find the fine-grained one. But in a very dynamic environment, it still needs to be seen. For example, a mobile kind of environment. Definitely existing.
So excuse me, so it seems that all the reviews we have used here is 11A3NG. So in which there is just single input and output.
Yeah, there's no end. It's just AVG.
Right. So if like in server 11N downstairs, or in router 11S. Which at a minor mode we enable. So how do you change the solution here? So is that the minor function good or bad for the
Well, I mean, the way I look at it is that it's giving me a radio link, right? And the same 802.11 protocol is running on that. So it's collision versus throughput behavior should be the same. Yeah, it will be more resilient to the interference that's given. Right? So your threshold for example, capture will definitely change, right? So, but as long as the same 802.11 DCS scheme is there, I think pretty much it can be applicable, I suppose.
Well, that actually is an interesting comment, because with 11N, we get the benefit of bursting.
Oh, sure.
Strings a bunch of
Sure.
packets together makes it more.
Yeah, no, the throughput figures should definitely be changing.
Well, that also affects your scheduling at the head end, because you might not want to think about single packets anymore.
Yeah, sure. No, I mean, those respects needs to be considered. But, the dependency of having higher workload, creating more collisions and trying to bring it down to an optimal level, I think that will still be relevant in this concept. So, okay, so the last one's here we saw no negative delay effect on the TCP, and actually the completion time for transfers were actually better. So we actually show that it's not only bubble, but it could also be implemented in practice. You see some gains, and also non-scheduled traffic can actually enjoy HeedNet also. Which brings me this single slide to just recap the conclusion over here. So I wanted to start with saying, across this, the workload assumptions are very critical. So in understanding how this thing behaves, so that's the way actually we started this thing, explaining two different takes on performance. So it still applies. So for our take as TCP-dominated internet type workload, which is typical for today, we've seen that having more clients in a high-density setting doesn't necessarily mean that your system capacity is getting down. Versus serving this workload, the same number of clients, with more access points is actually creating your trouble. We've seen, in our cases, up to 2/3 of the capacity being lost because of the increased collisions and uncontrolled collisions if you don't do anything. And so the insight we have was saying each access point, in this case, you're adding to the system, bringing 2 more active backlogged stations, if you will. And we proposed Wi-Fi as a contention window adaptation scheme where we could exploit this insight into number of access points being the driving force for backlog stations, and adapt contention window based on that versus previous work. And we also proposed HeedNet as an alternative scheduling technique on ISP, which could still reasonably recover similar amount of losses compared to a MAC kind of solution. This is sort of like layer 3 plus kind of solution, which requires client participation. I think this is sort of like the way I would like to conclude. You're more than welcome to hit me with any questions.
Is that a closed session?